We have analyzed collisions using the law of conservation of momentum. Now, we've done it in both one dimension and two dimensions, with 90-degree angles, with funny angles, like 35 degrees. What we want to do today to finish off our unit is classify collisions in a different way, not one-dimensional or two-dimensional, but rather we want to classify them based on kinetic energy before and after the collision. There are two types of collisions that we classify in this way. There are elastic collisions and inelastic collisions. An elastic collision is a collision in which momentum and kinetic energy are both conserved. Now, remember that momentum is always conserved. If you have an isolated system, momentum will always be conserved. But if it's elastic, so is kinetic energy. Kinetic energy stays the same as well. Versus an inelastic collision in which momentum is still conserved, because it always is if the system is isolated. But in this case, even if the system is isolated, kinetic energy is not conserved. Kinetic energy is lost. Now, when do we get an elastic collision versus an inelastic collision? Well, let me tell you a couple things. First of all, if two objects collide together, and we're talking about collisions here, not explosions, just collisions. If two objects collide together and they stick together like a lot of the situations that we've had have been. If they stick together, then it must be inelastic. Kinetic energy will be lost every single time if the two objects stick together. So if they stick together, you don't have to do a calculation to show that it's inelastic. You know that it will be inelastic. If the two objects bounce apart, in all likelihood, it's still inelastic, but it could be elastic if they bounce apart. So stick together, it's got to be inelastic. If they bounce apart, it could be either one, but probably still going to be inelastic. In fact, I would say if you're not sure how to figure out whether it's elastic or inelastic, guess inelastic, because 90% of the time you're probably going to be right just by guessing inelastic. Having said that, we don't want to have a 90% chance of getting a question right. We want to have a 100% chance of getting a question right. So how do we figure out whether it's elastic or inelastic? Do some calculations. Calculate the initial kinetic energy and the final kinetic energy. Don't set them equal to each other. Lots of people want to do this. Lots of people want to say, oh, just like conservation of momentum, EKI equals EKF, and then just do your thing. Why can't you do that? Yes, you do, but that still doesn't work. The point is here, we don't know if it's elastic or not, right? You can't set them equal to each other when we don't know if they're equal. They're only equal if it's an elastic collision. That's what the question usually tries to ask you is it elastic or not? So don't set them equal to each other. Okay. Let's get rid of this. EKI will be 1/2 M1 V1I squared plus, depends on how many objects you have, right? EKF could be 1/2 MVF squared if they stick together. Although if they stick together, you already know that it's inelastic, right? If they bounce apart, well, then you're probably going to do 1/2 M1 V1F squared plus 1/2 M2 V2F squared and get those two kinetic energies. If they happen to be equal, then good, it's elastic. If you've lost kinetic energy, then it's inelastic. It's as simple as that. Now, do we have to do this in one dimension and then in two dimensions? No, we don't. Isaac? Right here, this should be a 2, yeah. Right here, that should be a 2. Yeah, thank you. Why do we never have to do components for this? Even if we have a collision that's in 2 dimensions, why do we never have to do components for this calculation? Because kinetic energy is a scalar, right? It's not that you don't have to do X and Y components. It's wrong to do X and Y components. I don't care whether object number 1 is moving at 10 meters per second to the east and object number 2 is moving at 5 to the west. Make them both positive. I don't care if object 1 is going at 10 to the east and object 2 is going at 5 at 37 degrees south of west. 10 and 5. The direction is irrelevant. We're talking about 1 Fm times speed squared, not 1 Fm times velocity squared. Okay? So, if they stick together, it's inelastic. If they bounce apart, you got to do the calculation. If you got to do the calculation because they bounce apart, and EKI equals EKF, then it's elastic. If EKI is greater than EKF, in other words, you've lost kinetic energy, then it's inelastic. If you find that EKI is less than EKF, what do you know there? You've made a mistake. Okay, it will be one of these first two. Either EKI will be equal to EKF, it's elastic, or EKI will be greater than EKF, it's inelastic. If you find the third scenario, you've made a mistake. You're wrong. Yep. If they stick together, the kinetic energy, final kinetic energy, will be less than the initial, and it is inelastic. You just don't have to do the calculation because you already know that you'll lose kinetic energy there. That's correct. If they stick together, it's inelastic, always. If they bounce apart, it's still usually inelastic, but sometimes it's elastic. So if I said 90% of the time or so, it's inelastic. Like, when would you get an elastic collision? Well, first of all, they have to bounce apart, right? But not even, most things bouncing apart don't even give you an elastic collision. When I bounce a basketball, the basketball colliding with the ground is inelastic. Two cars collide and bounce apart, that's inelastic. Let me give you a couple examples of elastic collisions. If two billiard balls hit each other, that's actually not quite elastic, but it's really, really, really close. If two marbles hit each other, it's really, really close to an elastic collision. What's the difference when two billiard balls or two marbles hit versus the basketball on the ground or two cars? Okay, Peter's question is, if it's an isolated system, wouldn't kinetic energy always be conserved? No, if it's an isolated system, energy would always be conserved, not necessarily kinetic energy. Does that make sense? And we're talking about just kinetic energy here. So what's the difference there, Ollie? Yep. No, good guess, but that's not what it is. Notice? Okay, good idea, but that's not it. He said the ground can't move, whereas both billiard balls and both marbles can move. Chase? Okay, it goes against gravity, it comes back up. That's not the collision itself, though. That's after the fact. Okay, that's not it. Steve? Okay, momentum is more easily conserved. I wouldn't say that because momentum is conserved in both cases, the basketball and the marbles. Okay. Okay, you're on the right track here. No, not because it's made of the same material. You're more on the right track here. When we say they're harder, the billiard balls and the marbles are harder. You guys remember a law in Science 10 you guys learned? Said, anytime you do an energy conversion, second law of thermodynamics, anytime you do an energy conversion, you always lose a little bit of energy in the process. I know that's been 2 years, but you guys remember that vaguely? When you do an energy conversion, you always lose energy. When a basketball bounces on the floor, what happens to the basketball? It squishes. So kinetic energy becomes elastic potential. And then it becomes kinetic. So you got two conversions there. Kinetic to elastic potential back to kinetic. Guess what happens in both of those conversions? You lose a little bit. Due to what? Usually it's Heat. A little bit of sound maybe, but mostly heat. When two billiard balls hit each other, how much do they compress? Not much at all, right? So there's hardly any energy conversion, so there's hardly any kinetic energy lost there. Does that make sense? The only truly elastic collisions you get, like billiard balls aren't even quite elastic, but they're real close. The only truly elastic collisions you get would be subatomic particles colliding. Why? Yeah. No, if they stick, then it's inelastic for sure. Yeah. It's not so much the masses that we're concerned about there. Yeah, subatomic particles, when they hit each other, it's already as small as they get, right? You can't compress things that can't get any smaller, right? If there's no compression, there's no energy conversion, then it's going to be elastic. Does that make sense, Peter?